Good morning, everyone. Uh, did I mention that I did some re-recording of two videos? Okay, good. So just anyone hearing this, and I'm thinking the microphone I use is good quality, but maybe runs out of battery sometime. So if you watch a video and it stops the audio, let me know. I'll re-record that section as quickly as possible, but hopefully it doesn't happen again or often, but if it does, let me know right away and I'll revise those. I don't watch the whole video again. In fact, I don't watch any of it. Sometimes I just put it up there. So where we're at today is we're going to look at the binomial random variables, and we'll just take a quick peek at the pacing calendar to make sure we're on track. So that's this Friday. Oh, sorry. So we are here. Next week, we'll look at central tendency, which is mean, median, mode. So it's really getting more and more into statistics. And then we'll look at, so that's kind of where is the center of data. And then we'll look at variation or standard deviation, how spread out the data is. So we look at those two measurements. And then Friday, we can kind of finish up on things. And then this is really the application, the normal distribution. We're going to apply these things we've been learning, and same thing here. And then that's the end of the class as far as new content. And we have that whole last week to go back, review. We'll have some activities for you to do. But again, no new homework or anything, just things to help you do really well on that last test, which will be on Thursday, May 2nd. Okay, so that's our pacing. And the good news, at least I think it's good news, today's content is really nothing new. We've done all this stuff. We're putting together things we've already done and packaging them together to come up with this binomial theorem or binomial random variables. So we've talked about random variables. Remember when I introduced random variables, I said it was really nothing new. Rolling a dice, you get a 1, 2, 3, 4, 5, 6. It's just sort of saying, we're going to say x equals 1, x equals 2, and that's what the random variable is. So it's taking what we've already done with probability and sort of adding some vocabulary to it, maybe a little different way, a little abstraction. And sometimes that's the hard part, is saying, seems like what I did, but it seems different, right? Because they're doing it in a different way. Okay, let's just get into this. And then they give fancy names like Bernoulli trials. Well, why? Because there's some guy named Bernoulli who did this stuff. So first of all, let's break this down before we go too deep. Binomial, bi. What does bi mean? 2, exactly. So that's what we're doing is a binomial random variable is either on or off, right? There's only 2 options. You either pass or you fail. There's not a third. So bi is what we're doing. And so there's a probability of passing and there's a probability of failing. And again, it might be something different than those two, but again, you either this happens or you don't. You either go on the trip or you don't go on the trip, right? So that's the binomial thing. There are not going to be 3 options, only 2. So that's the key part of that. The word trials, Bernoulli trials, but trials is that these are going to be talking about probability experiments. And remember, a probability experiment is just something like rolling a die. That's an experiment. Let's roll a die and see what happens. Let's flip a coin and see what happens. Let's pull a marble out of a bag and see what color we have. That's what it is. And a trial, we're going to do those multiple times. Okay, maybe 2 times, maybe 3 times, maybe 100 times. But that's what Bernoulli trials refers to, as how many times we do that little experiment, how many times we flip the coin. Okay, so that's all that's going on here, is we're repeatedly doing a probability experiment, and the probability experiment always has an outcome of either pass or fail. And so we've been kind of doing that already with what was this? This was I forgot what this was. These tree diagrams that we did. What was the last formula we did? We were just talking about it, but I already forgot. Anyone remember? What's that? Bayes theorem. Thank you. See, you put somebody's name on it, and I don't know who Bay is. So anyway, the stuff we were doing with Bayes theorem, it's those. Most of those were Bernoulli, or sorry, binomial, because there was only either pass the test, fail the test, or something like that. There was a few we got at the end where there were three things that could happen. That's not binomial. Okay. So we're going to see it's very similar, but we come up with a little bit actually more simplified formula, tying in what we've done before with the counting and thinking about it. So Bernoulli trials and binomial random variables. Okay, so it sounds like a big name. All it means is the variables are going to be either, there's only two options, either pass or fail, and Bernoulli trials just will be, we do it multiple times. We flip the coin multiple times. So Bernoulli trial is experiment with two possible outcomes, right? Pass or fail, success or failure. And the probabilities do not change. So they're independent. Each trial is independent. Flip the coin, I got a 50% chance of heads, 50% chance of tails. I flip it again, I still have a 50%, 50%. Or we're going to see if it's not a fair coin, some coins maybe have a different probability, maybe a 40% chance of a head, which would mean a 60% chance of a tail. Okay, so we could do that. But that's the thing we're going to do. And then the second part of it is whatever the probability of success is. Let me change my color. That's not a very... Whatever the probability of success is, we can get the probability of failure, which we'll call Q, P's and Q's, right? By taking 1 minus P, 1 representing 100%. I like to think in percentages, right? So 100% minus whatever the percent of a success is, and it might be something. So if I have a 10% chance of success, I would have a 90% chance of failure. So we've been kind of doing this, right? Whatever the success rate is, the failure rate is the complement to 100. That's all this is. Okay. So we start if we could do this with a tree table, or tree diagram, not a table, tree diagram, where we've got P. And again, if P was equal to 10%, Q is going to be equal to 90%. And again, we could calculate that. We have to know one of those. If we know P, subtract 1 from it, we get Q. It also works the other way around, right? And then we can branch off from there. So this would be for one trial. Okay. And what we're going to do, all the binomial thing that we're doing, is we do multiple trials. So our tree diagram is going to get more branches. That's all. And you'll see, it's we'll build off of that. So far, so good. Okay. So here's the example we'll use. We're going to toss a coin 3 times in a sequence of 3 Bernoulli trials. Or we could roll a die and take success to be the event that you roll a 6. Okay. We'll do this one. Assuming a die is a fair die, the probability of rolling a 6, right, would be 1/6, because you either get a 1, 2, 3, 4, 5, or 6. And so there's 1/6 out of 6 possible equally likely events. And so then Q would be 5/6. So success, 1/6, failure, not to get a 6, 5/6. You roll it 10 times, then you have a series of 10 Bernoulli trials. Okay. And we just kind of do each one. And we're going to build off of that. Each trial is independent because you do it, the next one happens, it's got the same probabilities, right? The probability does not change. The dice, now again, if you're into chaos theory, maybe it does because you scratch the dice and now maybe the probabilities have changed microscopically, but we'll just say that in our world, for what we can examine, probabilities are not changing. Okay, so we have a binomial random variable is the one that counts how many times we get a failure or a success. So we're going to look at a few of these examples. So the binomial part would be, okay, 3 Bernoulli trials. So we get either a heads or a tails, right? Heads, heads, heads. We could get that. Or we could get a heads, a tails, and a heads, and so forth and so on. And we might set up x to be the number of heads. So in this case, x would be 3. In this case, x would be 2. Okay, so that's we assign. So that's what we do. So there'll be an assignment. How is this random variable being generated? And usually it's how many successes we got on the number of trials, right? 3. Wait a minute. Yeah, how many heads we get. So this would be if we set it up to be how many heads, and this is x is 2. We might have heads, tails, tails, and then x in this case would be 1 head. And we obviously we got all tails, and that random variable would be x equals 0. Okay, so we'll do that. So we're going to visualize it. I think this is where we get into our sort of our example shortly after this. So what's happening if there's 3 trials? We just getting more and more branches. And you see how the 4th trial, each one of these would have 2 things coming off. So it gets various things. But this a success, success, success. So we say there were 3 successes, x equals 3. Success, success, failure. There was only 2 successes, so x equals 2 for this one, and so forth down the line. Okay, so this is all we have to really keep in track of for this whole thing. It applies to many different things, whether we're actually taking a test, whether we're flipping a coin, rolling a die. It's we label something as a success and then something's a failure. Okay, so it's narrowing it down. It's not just the probability of getting a number on the dice or something. It's very specific, but it will always look like this. And again, this probability over here, P, once we know that, we can get Q because that's going to be 1 minus P, right? It's the complement. So they're kind of cool. Now, it's weird because if it's 50-50 chance, right, both P and Q are 0.5. So it's hard to talk about those because it's which one is P, which one's Q. They're both the same. So we'll look at an example where we don't have a 50-50 chance of something happening, or so we'll, like rolling a die is nice because that's a 1/6 chance. X is the number of times you roll a 6, right? If you roll it 3 times, then x is equal to 3. If you roll it 2 times, it's equal to 2. If you roll it no times, you don't ever get a 6, and x is equal to 0. So it's tying together these 2 types of theory. So it allows us to basically turn everything into a number we can use. So let's look at a specific case. We're going to see how we would calculate these probabilities specifically, and then we're going to generalize it into a formula so that we can use it for any case. So here is our story. We have an unfair coin, which means it's not a 50-50. But they don't tell us what it is, and for this case, it's not so important. We have an unfair coin. Probability of the heads is P, and probability of a tails is Q, which is 1 minus P. Okay. And again, the actual probabilities are not as important, but we could, we know it's not fair, so it's not going to be 50-50. What we're going to do is take X to be the number of heads you get in a sequence of 5 tosses, 5 flips. So we're going to flip this coin 5 times. And every time we get a heads, we count that as a success. And then that's going to ask us find out what we would get if X equals 2. So how many different ways can we get 2 heads? And I remember this, we sort of did something similar to this What do we need to do first? We need to count all the ways we can get 2 heads, right? So we have to start listing what are all the possible series of 5 flips, right? We'll take a look at one because that would probably be a fairly large list. Certainly we get 2 heads and followed by 3 tails. This would be one example of 2 heads, right? Flip the coin 5 times, get 2 heads. That's called a success because that's what we're looking for. So let's see how we would calculate this particular one, and then let's use our counting stuff that we came up with to figure out how many times we'd have this sort of thing happening, but possibly in a different order, right? Because if we got heads first and then 3 tails and then a heads, that's still 2 heads, but the order is different. So we're going to use combinations with these. So what's the probability of getting a heads? It's not a number, but it is given to us. P, whatever it is. Could be 40%. We don't know. But yeah, so probability is P. And remember, this is these tree diagrams. So we got a probability, we got a 2. And then to the next tree diagram, we get another 2, or sorry, not 2, we get a heads. So we're multiplying, right? So the probability of getting the second head is what? It's also P. Right? So the first head probability is P, second one is P. And this is the multiplication theory, because that's how we do those tree diagrams. We multiply along each branch. So this takes us right back to Bayes' theorem, what we were doing. Same thing. Then we get a tails. So this is what's the probability of a tails? Not P. 1 minus P. Or to make it brief, you could put Q. You could do either one. We could put 1 minus Q, 1 minus P, and it'll be accurate. And then the fourth tails happens because there was a probability of Q, and the fifth tail was a probability of Q. And so this probability of this particular thing happening is P squared Q to the third. Okay. And if they gave us what P and Q were, we could calculate that. But that's only that possible way because of that order, right? Because when we count probabilities, while order wasn't important in what we're looking for, it does say that that was one event. So we've got to count all the events where we get 2 heads. That'll be the next step. But this is basically just would give us the probability of just that one heads, heads, tails, tails, tails. Does that make sense? Does that seem reasonable? Maybe. Okay, we'll keep going. And the reason we can also multiply is because they're independent events, right? We don't have to get that off. So that's what they came up with. So it was already written, but I just wanted to build it up. So that's that one. Now, how many different ways can we get that? And again, it's in the next slide more critically, but remember from the last test, again, we're not directly testing you stuff on it, but we're using stuff from the last test. Think of this as a code with 2 letters. How did we calculate the number of ways we could get a code with repeating letters? Well, this one, we could say we're wanting to get 2 H's, right? It's got 2 H's and 3 T's. So the way we count the 2 H's, there are 5 trials, and we want 2 of those to be H's, and they can go anywhere else, right? Now, there's also one more we would multiply the 3 tails, but that's always going to be 1 because there's only 3 left, and we want 3. This doesn't show up in the formula for that particular reason. So we would say we've got 3 left, and we want them all to be tails. This 3 choose 3 is one way to do that. Okay, so you won't see this in the formula, but just think of it, it's sort of there. You'll see this in the formula. That's how many different ways we can flip a coin 5 times and end up with 2 heads. Okay, so that's from that counting. And again, look back to the test. We had some words in there. I remember Arkansas was one of the words, and we calculated what are the number of ways we could rearrange it. So that's kind of what's going on there. And so that's what this is going to say. We've really already talked about this. HHTT is only one of several outcomes. There's these. And how many different are there? They're writing it this way. If five, choose 2. I like to do it this way. 5, choose 2. And it's equal to 10. And again, I'm just going to remind us how we go about calculating that. Let me get down. Let's see, where is my, here it is. Remember, to calculate that, we can enter the number 5. We go to the math, because this is what we're going to use. And it's always going to be, in this case, a combination. And we want 2 of them, 2 of the 5 trials to be heads. And there it is, it's 10. Okay, so, but see, now we can generalize this. If there was 50 trials and we wanted 35 of them to be heads, that would be a messy tree diagram, but we can figure it out from here. Okay, so there's 10. Let's see, let me get back. Uh-oh, where'd it go? There it is. Okay, so that's where this is coming. That's where that calculation comes from. We go to our calculator and we just do it. And so that means the probability, remember, we got 2 heads, which is a probability of P. We got 3 tails, which is a probability of Q. And then this is going to happen 10 times. So we're going to multiply it by 5, choose 2, which is going to be 10. And because what's really happening, since each of these outcomes they each have the same probabilities, we're really adding them together. And when you repeatedly add something together, that's what multiplication is. So we would add them together 10 times, but it's a lot easier to just take it, multiply it by 10. That makes sense? Kind of. And again, we're going to give you a formula, so even if you don't understand it, you can say, okay, I plug these in, I get my answer. Oh, okay, it works. So we approach this from several different angles. Sometimes just give me the formula, I'll calculate it, and we'll trust it. But this is just so kind of to build. Hopefully, after a while, you'll see, oh yeah, now I see what's going on. But for me, it always took a little practice. So that's, again, what they give us. We're going to calculate how many different ways it can happen times the probability of one of the things happening. And they give us this sort of in-depth thing of what's going on. This 5 is the number of tosses, the number of Bernoulli trials. So again, if it was 50 trials, this would be 50 instead of 5. 2, the number of heads, the number of successes that we're looking for. So if we were looking for 35 successes instead of 2, it would be 35. And then what you see is that these exponents always have to add to the number of trials. So 2 plus 3 is 5, because there were 5 trials. You'll always see that. So if there was 50 trials, you'd have to add those 2 exponents together to get 50. Okay, so it's just like, once you know one, you can figure out the other. There's always this thing of complements going on. And P is always the complement of Q, or vice versa. You know, they're all going to add up to 100. Whatever one is, the other will get you the rest of the way to 100%. So all that changes is how many trials we did, what the probability of a success and a failure is. Those will change, and we would plug those in if we needed to. And what else changes? And what we call a success. Is it 2 heads? Is it 5 heads? Is it 30? So that's all that's changing on us. So it makes it very easy, or relatively easy, to make this generalized. So X is the number of successes in a sequence of, and again, we just sort of in Bernoulli trials. So this 5 would also be N, right? That's what we're going to generalize it to. And then here we go. N comma X, we want this many. And again, they're telling us how many successes we want. That's going to go here. And P is our success rate. So P to the X, that's how many successes we had. And then Q is the complement. n minus x, right? So we'll do an example here, but basically you can just plug everything into this formula for the most part. Look, there's only, I think, 6 questions, maybe 7. There's not too many of them, but they'll give you the percentages of success, how many trials, how many successes they want. You plug it in, you're done. There's 5 of those questions. I think the last one's a word problem. I looked over it. You just have to pull out from what they give you. You pull it out. I'll give you that one. Okay, and that's what's going on. N is the number of trials. P is the probability of success. Q is the probability of a failure. So let's take a look at an example. So if you roll a fair die 5 times, the probability of throwing exactly 2 6s. So it's kind of similar to what we did, but a little different, right? So how would we calculate that? First of all, what is the probability of a success? Success is you roll a 6. What's that probability? And it's only 1 die. Probability of rolling a 6 on a fair die. 1/6. Good. So not bad. So P is going to be 1/6. So what is Q going to be? It's going to be 5/6. They don't make nice decimals because they're repeating, so we'll just leave them as fractions. And I think it sets it up. But so we're going to do this 5 times, right? And we're going to throw exactly 2 6s. So that means that what we're looking for is that the random variable is equal to 2. So what's the probability that the random variable equals 2? It's the same thing as saying what's the probability of getting 2 6s when we roll the dice 5 times. From the formula, we know we've got 5 times. Choose 2 successes. So that's going to be how many times? We've actually already done that. That was 10. We could plug it in again. And then we're going to get the probability of P, which is 1/6. How many successes are we looking for? 2. So that's an exponent. And then 5/6. I remember doing these. I go, man, this seems weird. And the way it was explained to me, I never figured it out. But whatever. If you know P, you know Q. 5/6. How many failures are we going to get? 3. 5 minus 2. And now we just need to calculate that. And that's going to give us a probability of getting 2 6s. So you see how we've sort of done stuff like this before, earlier in probability, but we just phrased it differently. We thought of it differently. We maybe had to do it more by hand, but now we're getting sort of these shortcut methods, which are sometimes helpful because there's a formula and you do it, but then it's also abstract. So sometimes we don't really know we don't have a gut feeling for what we're doing. So part of this is getting, if you can connect it to the actual what's going on, and think, okay, I'm rolling some dice and getting 6, and got 2 6s and 3. I got something that are not 6s. Okay, so the probability is actually 16% for that to happen out of 5 trials. Yes. What's that? The failures are Q. So in our formula, our successes are power of 2, and that's wrong. Oh, yeah. So, I gotcha. So yeah, so if there's 2, because there's 5 trials, so we could think of this 3 as being 5 minus 2. Yeah, thank you. So it's always going to be that complement. So that's important to know how many trials there were. If there were 6 trials, then it would have been 4, right? So it's always that complement. Good question. Just a little dense sometimes, especially on Friday, because think about the weekend. No, I just work over the weekend anyway, but good. And so we could do the calculations, and we go from there. And that's all there is to Bernoulli. So most of this lecture was about trying to understand the formula. I could have just started, here's the formula, do it, and some of you would have been just fine. But I wanted you also to understand that it's bringing in 2 different days of our work, right? We did ways of counting, and maybe that was like 2 days of stuff, but combinations, and then probability. And again, all we used is, there was n trials, so 5, so 2 plus 3 have to add to 5. The exponents always have to add to the number of trials, right? And then this is telling us the number of successes, so that's always going to be there. And it appears there, and we're able to calculate. And that's the end of the lecture. In the homework, what you're going to see is they're going to give you different numbers for n, different numbers for p. You'll need to calculate q, and that's actually all they need to give you. They'll have to, except they'll also have to tell you how many successes they want. So in this case, they told us 2 successes, right? So somewhere, we use this, and so that doesn't say it, but they would have to tell you somewhere where they want the random variable to be 2, which means 2 successes. 2 successes and 3 failures in this case. So again, once you know one piece of the information, you find the complement, and you always know the other piece of the information. Success, failure. It's really cool. And a lot of our world can be thought of in this fashion. Not everything, but a lot of things can. Okay. Questions? Not too bad. We're done a little early. So, and we've got office hours if you want to stay and work on things. That's great. Next week, we get a little more heavily into statistics, which is mean, median, mode. You may have seen some of those things. Again, we'll probably bring back some of the things we've done. Wednesday is standard deviation and variation. So things that you'll look at, we've done before. Probably, maybe not in this class, but another class. And then we'll have a break on Friday. So opportunities to get on track. Remember to take a look at the review worksheet that's there, just to kind of see what those question types, as you do the homework. Don't have to work through it, you can, but keep that as your eye, because that's very likely, I haven't seen the test yet, but very likely what the test questions are going to be sort of formatted towards. So keeping track, doing the homework, getting those, and you'll have great success as we move forward. Awesome. So take care, stay safe. It's a jungle out there, isn't it?